Good day. I am Idris Zakariyya. I am one of the author of our paper titled Robust, Effective, and Resource Efficient Deep Neural Network for Intrusion Detection IoT Network. And this paper is going to be a fair on the proceeding of Cyber Physical System Security Workshop 2022. And the main message of this paper is how to exploit deep neural network in terms of robustness and effectiveness in IoT resource-constrained environment. As we are aware that IoT consists of limited resources, limited computational capability, and limited battery. As a result of that, most of the security solution or AI technique that are being utilized for mainstream IT devices cannot be directly used in IoT environment. As a result of that, they need to be optimized for them to be scaled through IoT resource-constrained environment. So we have started with this is the overview. This is what we are going to cover throughout this presentation. We have started with the background and what is all about this research, and also what is the motivation behind this exploration, and some of the methodology we have tested, and most of the experimental evaluation and the finding we have from this research, and also conclusion and the future research work. As we can see that Internet of Things consists of connected physical device. IoT serves as an ecosystem used in smart homes, smart city, and many autonomous intelligence systems. And this IoT consists of many different physical devices that join together from the network of Internet of Things. As we can see that by 2030, the number of devices to be connected on this IoT has been projected to reach about 125 billion. And this is a very huge number. We have more devices connected to the internet, and this is showing the importance of IoT and also the fascinating capability of IoT devices. And this IoT use embedded system such as processors and also embedded hardware to collect sensory data. IoT are used in collecting sensory data in hospital in different domain. And you can see by 2025, a significant amount of data being projected to be collected using this IoT device, about 79.4 zettabyte. With this, you can see that IoT devices are fascinating and advantageous device in the society that need to be secured against the bad attack and against various cyber attacks. Despite all this capability of IoT in collecting sensory data using the processor and embedded devices, and used in many automation and with huge number of connected devices, bad guys are exploiting this IoT device for different purpose. Because of that, IoT, they have a lot of vulnerability and security leak among these IoT devices, and this vulnerability leak dynamically increasing. As you can see, the 2026 DDoS botnet attack launch, it caused a tremendous disaster as many companies, including Netflix and Twitter, has been affected by this attack. And one issue to be considered also is that IoT have low computational capability, low computational power, low memory, a low processor. As a result of that, most of the attack, most of the security mechanism need to be proactive and effective in nature. And so because of that, existing security solution utilized for mainstream IT device, the machine learning and AI technique can scale through mainstream IT device cannot be able to utilize the same machine learning or AI techniques in IoT device as a security measures. Because of that, we exploit the deep neural network, and this deep neural network, deep learning, outperform traditional machine learning algorithms in terms of accurate classification in various domains. And deep neural network also offer a promise in cybersecurity monitoring as it perform a lot of traditional machine learning method. One disadvantage of this neural network is that it requires a lot of training data, larger training data, a lot of multisensory data for it to perform accurate detection, accurate classification. So this is a problem in a resource-constrained environment, because as the number of data requirement increases, then the training complexity increase. As such, the computational expense also increase. As a result of that, such training method utilized for mainstream cannot be used in an environment such in a resource-constrained environment such as IoT. And for this reason, deep neural network that can be deployed to IoT need to be resource efficient and effective in nature. And one disadvantage of deep neural network is that it can easily be crafted with adversarial sample. So because of that, we have investigated a series of research questions. Can existing deep neural network be trained to be resource efficient in nature so that it can be utilized in a resource-constrained environment such as IoT? And can the resultant deep neural network be robust, well resist against state-of-the-art perturbation method? Now we investigated the typical fully connected neural network, and we have started with the baseline fully connected neural network training, where we use the normal mini batch gradient training, and we take measures of the memory consumption to compare with our proposal in the next algorithm. So the next algorithm too is the proposed method we use to obtain the REDN. And this is the proposed training method that can be able to give us a lighter version of resource efficient deep neural network. As we can see, we utilize a number of techniques like simulated micro batching, and also like weight penalty, where we shrink the network in order to get a lighter architecture. And one good thing about our model is that we incorporate the memory constraint in algorithm 3. As you can see from line 9, we call algorithm 3. And this algorithm 3 contains the memory constraint incorporation and time constraint incorporation. As you can see, line 4, we estimate the memory after after relaxing the penalty parameter, and also estimate the time. Then we integrate this memory constraint and compare with the previous iteration and see if the integrated memory is increasing or memory is not improving. Then we also record that memory at that particular point as the efficient memory. And if also our incorporated memory is still lower than the previous memory, then we integrate it as the efficient time. At the end of the day, we return the model with the efficient parameter and the lower error than the previous baseline model. Now we have tested against a series of attack here, a series of data set where we can see most of the techniques available in the literature. They are using general purpose networking data set like KDD and a lot of other data sets. So in this aspect, we consider data sets that are device specific, that are from IoT device specific, like doorbell, security camera, Samsung, Philips, and so on. All these data sets have their own distribution of normal and attack. And because we utilize them for the task of binary classification, as you can see, the output is 1. And we have used a different number of parameter search algorithm in order to find the best utilized architecture that can be used for both the optimized REDN and also the baseline FCN for a peer comparison. Now we have checked the effect of robustness against our network. As we can see that as the number of epoch increases, the resilience of both the baseline and the optimized version increase against the state-of-the-art perturbation method, like the path gradient sign method, projected gradient descent, and also the noise. But as we can see that even in each number of epoch, the optimized version demonstrates better resilience compared to the baseline model. And this is good, as indicates well resistance and better performance compared to the baseline counterpart. Now we have seen how we can be able to show the resilience against reduced hidden architecture, as we can see with against resilient against hidden architecture. As we can see with 50% neuron, reduced neuron, the optimized version is better. With the blue line, you can see it show a better accuracy compared to the baseline. At the same time, when we reduce the neuron by 25%, also the optimized is even better than the baseline in terms of the FGSM pass gradient sign method and also the noise attack. We also demonstrate the importance of our method, not only saving resources during training, it can also save a lot of good resources during testing. And this is good for an online detection, because if you are looking for a method that can be able to detect attack online, it needs to be resource efficient, so that because of the limitation of IoT, limited computational resource, therefore, technique deploys to IoT need to be resource efficient in nature. So you can see that now we have saved a number of resources using our own method compared to the baseline. We're using the inaudible device centric data set, we can set about 77.63% of memory while achieving the same accuracy with the baseline. And this is also a very good saving without accuracy degradation. Now we have compared our method against state-of-the-art performance technology, because in our technique we utilize NumPy, and we show that even with NumPy you can be able to build a better model that performs state-of-the-art framework. And the building the technology using NumPy is very good, because it does not require any library, and it can give the audience a sense of what is happening in the internal architecture of the model. As you can see now, we compare with Keras, the TensorFlow Lite, and the NumPy, and all our model in NumPy, the resource efficient is better than the rest of the model while achieving the same accuracy. Even though the TensorFlow Lite that utilize the quantized TensorFlow Lite that utilize plot system precision is slightly lighter than our model, but in this implementation we didn't consider the plot system precision, because plot system precision can cause numerical issue and at the same time can degrade accuracy performance. Because of that, we utilize plot 32 in table 4 to compare both each framework and report their performance. In table 5, we compare the performance in terms of testing, that is the dual detection for the testing data. As we can see, our model consume lesser time and lesser memory compared to the other framework, while achieving similar accuracy using the PT737 device-centric dataset. Now we have checked the resilience against using integration with plot system precision. As we are aware that plot system precision causes numerical issue and reduce accuracy, but we now integrate it in the table 6 to show that even with plot system integration, the error radian is still better than the FCNN, its counterpart, especially in the detecting the pass gradient sign method and also the noise attack. Now in table 7, we compare the performance of our method using the pooling the poison level attack. And with the poison level attack is if you have a level that is 1, you change it to 0, and you have a level that is 0, you change it to 1. And even in that particular scenario, this SVM support virtual machine, the gradient boost, and other boosts, and even the baseline model, all of them have been fooled by the level flipping attack, but our model can still provide a standard accuracy while with the level flipping attack better than each of the tested framework. And this can be result of the regularized parameter and also utilization of efficient method. Because of that, our model cannot be able to be scaled through overfitting, while the FCNN without the regularization can be overfitted, and that's why our model that is less complex provide a better resilience compared to the other model. In this paper, we have exploited deep neural network and to propose a reliable AI security method for intrusion detection IoT network. And our method is robust and resource efficient, as it outperforms most of the state-of-the-art techniques as compared and reported. And the technique can detect accurately detect adversarial attack from each IoT device that I said. It demonstrates more efficient performance than in quantifier in terms of robustness and resource consumption. And the resource saving advantage of our method is good for on-device learning, especially in pediatric learning using decentralized edge devices. And also the efficient detection is good for online detection using multiple edge devices. So if you need any further explanation, you can be able to read our paper. It contains the experimental in more details, and also it includes all the GitHub code for this work so that it can be able to explore for further future references or for application. Thank you very much. Thank you for listening.